As I said, my name is Miguel. The company EMS is in Barcelona, and we are running Seabird Electronics representation in Spain, France, Belgium. And we already operate more than 28 years in the oceanographic market. And we serve primarily our customers in the south of Europe. We work with Seabird Electronics, but also with other companies, the classical blue ocean oceanographic equipment companies. And we are not only commercial representatives, but above all technical. We know the products we sell, we know how to use them, and we are system integrators. So we are used to put them out in the field and provide solutions to our customers. We also do a lot of international projects related to the countries we are in. So we have been in the Middle East and Latin America, lots of different places. And today I'm going to talk about this Seabird product, which has been existing a long time in their catalog, but I think it's kind of a bit unknown and undervalued and unexploited. But it has a lot of potential, and because it's a product that needs a little bit of integration work, you need to know how to use it. Well, it's not one of those things that you just buy and push a button and it works. So you need to know how to integrate it. But we are happy. We and the people from Seabird and other experienced users, we are happy to share our knowledge with you and explain you the little details, because there's where the trick lies. So the title of the talk is Real-Time Moorings Using Inductive Modem Communications. And I'll explain what this is. Is there anyone that has already experience with inductive modems here? Okay. Everyone else, the others, they don't know, have heard about it? No? Okay. So those are the discussion topics. I will run through it and I will explain around it. And if you have questions, it's not going to be a formal talk. If you have questions, just raise your hand, ask directly, and we'll address it, okay? So first a little bit about the technology basics, components, then a little bit features, so you can identify the different parts. A little bit talking about how to use the instruments for communicating, and then examples. There is an application note on the website, number 92, which is a little bit the literature about this theme. So the idea is to provide a technology that allows you to do real-time communication underwater. And the basic idea about inductive moorings is that it's very simple and very robust and quite cheap compared to the alternatives, which would be kind of hard wiring, directly connecting wet connectors or connectors, multi-conductor cables. After 2 or 3 instruments, it's a mess. And then there's also the acoustic telemetry, which maybe you know that it's kind of power consuming. It's also not so reliable because you depend on the environment, on the sound within the sea and the water. And so the inductive moorings, they use just a metallic cable with a plastic jacket. Okay. The motivation is, of course, to have a high spatial and temporal resolution in the ocean, in the water column. But from the beginning, I will tell you that you can use inductive moorings or inductive telemetry not only vertically along a mooring, but you can also use it with a cable lying on the ground. You can use it horizontally. You can tow a cable behind the ship. You can lay a cable, kilometers of cable on the floor, on the sea floor, from the shore to the open ocean. You can clamp instruments to it and use this telemetry. I will explain how it works. But the main motivation was to have deep sea moorings with a lot of instruments to get a good horizontal resolution. with a simple way of manipulating and maintaining the system. Yeah, so basically what we will see is an architecture of a buoy in the surface and then a metallic cable with instruments clamped to it. So it's a hardwired, as I said, it's hardwired. Hardwired telemetry is what I explained before, using multi-conductors. It's completely out of question. You can do it if it's just under the buoy for one instrument or a few instruments, if you have short cables. But if you have a long mooring cable, there's rotation and twisting between the buoy and the mooring cable. If you go deep, you want to use inverse catenary moorings. So there's a lot of dynamics involved with the mooring line, and so you cannot have a multi-conductor cable. I know that there have been experiments and some people that have been developing, high technology multi-conductor cables, even with fiber optics. There are cables out in the market that can stretch with multi-conductors, but this is very expensive, and also it's complicated. It needs a lot of maintenance. It can be interesting for certain situations, but this solution, what we offer with inductive telemetry, is very robust and very simple, and is proven. It has been being used for decades now. So let's go a little bit to explain the basic principle. This is a oversimplified explanation. It's basically electromagnetic induction, so it's the Faraday principle. When you have a dynamic electrical, an electrical charge which is in movement, which moves, it generates a magnetic field which couples again with another electric field. So you know that the electric field couples to a magnetic field and then progresses along the conductor or along the space. So what we do is using this Faraday principle, using a dynamic electrical signal to induce currents remotely. So the way it looks is that we translate this to an underwater mooring line, taking advantage of the fact that we are underwater and seawater is conductive. The fresh water is also conductive, just a little bit less. So it also works, this system also works in fresh water. Most of people use it in salty water. The only difference is that you need to, if you are in fresh water, you need to make the ground bigger. I'll explain. So imagine, this is not a great drawing, but I will try to explain. So imagine this is underwater from here. This is the surface buoy, and you have a cable which is jacketed. This black part is it's supposed to be the cable jacket. It can be a plastic jacket. So it's just a metallic cable, a galvanized iron or whatever metal. Normally you should put galvanized iron in the water, but it works with any type of metal. And you need a plastic jacket. The quality of the plastic jacket is also important. Those are the little details which are important. If you do the operations, you have to know what material to use, which manufacturer, So that's where all the little details are very important. But here's the principle. What you do is you peel off a part of the jacket at the surface. It's still underwater. Here's the water surface. And you need another part peeled off at the bottom. So those metallic parts are touching the seawater and making electrical contact with the seawater. So there's a ground. You can imagine this is kind of ground, and this too. So it closes basically a loop. So if there's a current flowing through this cable, a signal, then you can close the loop, right? So What we do now is to clamp instruments that have conduct inductive toroids on the jacketed part of the cable. And then you can induce telemetry. Okay? So it looks like that. Down at the Seabird booth, you can maybe see some instruments. And what we have done at Seabird is we have repacked a classical Seabird instrument like this Seabird 37, and instead of having here a connector to connect through the serial connection, what we have here is this part, which is what we call an inductive coupler. It's I will show you now pictures how it looks like. And in this part, you can see there's a little hole here, so you can put a cable through it. And this part has a ferrite, a metallic, highly conducting magnetic toroid in it, which is able to induce a signal onto the cable. Okay, so you run a cable through this little hole. This part is just a clamp for holding onto the cable, and you can induce a signal. I'll come to the details later. So this part here is another type of piece of hardware, and this is normally used at the surface to connect the inductive signals that are coming from the instruments down below, to decouple those signals through the same principle with this inductive cable coupler or decoupler. And basically it converts this inductive signal into an electrical signal that you can connect to the data logger, to a multiplexer or whatever. I'll come to the details. So the way it looks like is this. That could be a typical architecture of an inductive mooring. But remember, you can do the same horizontally lying on the ground, okay? Or just, you could imagine it floating in the water somehow, or being towed by a ship through the water. So you have the surface buoy. Inside there's the electronics that basically, the data logger, the different converters or whatever. And then you have here the mooring line with its weight here. And this represents what I told you before. This is the jacket. And then you have the parts that are metallic without jacket, which you need to peel off or take away the jacket. You don't need to take away much length of it, just, like this. Sometimes a shackle will do. And it's important that you have this electrical architecture, that you have a good ground here, and at the end of the long cable, you have another good ground. So you close the telemetry loop, okay? So you get this, you put those instruments, you clamp them on the jacketed part of the cable. Along the cable, you can put hundreds of instruments along the cable. It's just losing a few screws. You can move it along the cable. So it doesn't have to be at a fixed position. You can just, select it manually. Or there's people that has invented ways of traveling along the cable, with those McLean profilers and other types of vehicles, that if you maintain the closed loop through the cable, you basically can travel up and down or along the cable, and still there is induction and inductive telemetry. Because the instrument doesn't know where it is along, there's no way of knowing the position along the cable, only if there's a pressure sensor, obviously. So you have the instrument here coupled to the cable, and then here at the surface, you have this surface coupler. That's the part I showed you before, that basically decouples the inductive analog signal and feeds it into a controller, okay? So again, each instrument that has an inductive modem integrated can be put on this cable. We also have inductive modems that can be connected to whatever serial instrument. So you can have an ADCP or whatever instrument or system that provides an RS-232 signal. It can be connected to an external inductive modem. Seabird has those components. And so you can basically adapt whatever type of instrument to an inductive mooring line or inductive line. So here a little more detailed graphic. Here you can see a little bit how the instrument is wired. So imagine this is the Seabird 37. It has the two wires of the electrical signal that is wrapped around this ferrite toroid. This ferrite toroid is split in half. So there are two halves. And if you touch them together like this, they close the loop, So that's the trick that we have to be able to put it onto a cable, right? You can open it and then put it together. So the electrical signal is, you put those, you wrap the conductor around the ferrite toroid. So you have an electrical current and induces a magnetic field that on the other side induces an electric current onto the cable. So the signal is transferred analogically by induction from the instrument over the toroid to the cable. Okay, and we use basically what Seabird uses is simple frequency modulated signals. It's an analog signal. That's the downside of it. It's not a high bandwidth signal or something like that. It's a 1,200 baud transmission rate. And because it's an analog signal, it has to be sequential. So each instrument has to talk at one time, okay? But nevertheless, it's still very convenient. You just have to make sure that the instruments talk, don't send too much data at the same time and so forth. That's something that the electronics and that the data loggers, the Seabird loggers can handle and are designed for. And very important, its power consumption is very, very low. That's very good because you can leave this out in the field for years and it will work. So you induce the signal onto the cable and you can sense the signal at whatever position along the cable. So if you decouple the signal at the surface, you can feed it into the buoy. You can also decouple it here and feed it into an underwater data logger. You can do what you want. So the different signals of the instruments are coupled onto this cable where you can transmit along the cable. So each instrument has an identifier and a specific tag. So you know who is transmitting when. Okay. So this is the way it looks. So this is a real hardware. So those are those white brackets that you see on the instruments that sometimes are integrated onto the instrument, but you also can buy them separate with just a cable to connect to a serial signal. And inside you find those ferrite toroids. It's the same material that you find sometimes on the power plugs and stuff like that. It's a highly magnetic, electromagnetically conducting iron material. It's very delicate, so if you drop it and it falls on a hard ground, it will break into pieces like glass. And that's one of the problematic things, yes.
Is it like a magnet?
It's not magnetic, but it's ferromagnetic. But alone, it's not magnetic. It's good for electromagnetic induction because it conducts the magnetic field very well, so you don't have signal loss. So again, here for the practical side, this is a very delicate part. So if you drop it, if you do an operation on deck and you work around with instruments on deck while putting them into water, you have to be a little bit careful. They are protected inside this plastic thing, but if you drop them really hard and so, it can break. Although they are confined inside this holding plastic Delrin piece, if they break inside, you lose efficiency, you know. And sometimes a little piece breaks off here, and then the contact surface is not the same and not perfect. So you have to be a little bit careful with handling those things. It's a trade-off, you know. So if we take out those two half toroids from this piece, you will find this. You can buy them as a spare, and then mold it into the, you know, molded into the Delrin piece. We have those coils which connect to the cables to the instrument signal. So the analog signal comes through here and is induced. Here's the current, here's the magnetic field, and then you induce a current onto the cable that runs through. Okay. So again, you have the instrument with, here's the toroid coupling the signal onto the jacketed part of the cable. This is just a holding bracket. There's a lot of people who is not trusting those original brackets, because if there's a lot of rough handling on deck while deploying or while recovering, you want a little bit of extra protection. So you will find photos on the internet from the groups that are deploying inductive moorings, that they have an extra protection around the instrument because of the handling, you know. And sometimes it can be very rough. Some of you know it. So you may want to add extra attachment, you know, extra security and so forth. But that's something the manufacturer doesn't go into. You know, this is we leave this over to the customers. But it's good advice, maybe, you know. But it works like that. But you have to be more careful, right? This is the signal decoupler. So here, it's not, you cannot see very well here on the picture, but it's clamped onto the jacketed part of the cable. So the peeled off part is always over the last inductive modem system. And then you have the cable that you can feed into this surface module. We call it inductive modem module. That is basically the electronics that converts the analog signals to the digital stream RS-232 that you can feed into a data logger. Okay, so this is a converter from inductive signal, which is a sequential analog signals into a stream of digital of one digital stream, which you have basically separated by commas and identifiers, the different instruments and the different strings from the different instruments. Yeah, so in the surface, you can choose whatever buoy controller, whatever. You can use Campbell, you can use whatever you want. And then from there, you can send it to your telemetry system with all the different options you have on the market. This is the IMM. This is a Seabird product you can buy. It's a very small thing. It's half of this telephone. It's like this. It's really very small. And the idea is that you can integrate it very easily because it has this small footprint into whatever instrument. There's always a little bit of space, or you can use a small housing. So you can put it into the buoy with a buoy controller, or you can put it inside an underwater housing. So this thing is what you use if you want to convert your instrument into an inductive system, because you need to feed into here the digital signal, and then you will get out through those two pins the analog signal that you can induce onto the cable with this ICC or this coupler component. Yeah. Yeah, here. Yeah, I can. You can have a look. So this is here this is exactly the IMM that you see on the picture, but inside an underwater housing. It's another catalog item. So you can buy just the electronics with the seabird housing, with the connector. And then you have, here's the clamp. Here's a normal clamp, it's just a mechanical clamp. And that's here the toroid. And the toroid, you could see it here a little bit through the delrin, the two halves of the toroid. And this is the machined part of the housing that we fill up with resin, with the cabling, where you would find the coils and all that, you know. So this is one of the catalog items. So you can have all the different versions. This is a Seabird 39 temperature sensor with pressure. With the same thing, Seabird just integrates this cap, this inductive modem thing here. So you can just put it onto a cable directly. So this is mechanical, and this is the inductive part. The same with the 37. It's the same. It's a classical 37, and with this part on top. You know. Yeah, important to understand that inductive telemetry is an analog system, very low consumption, but it is sequential. So you can only talk. There's only one instrument that can talk at the time. So you need a buoy controller that pulls different instruments, like number one, tell me your temperature, then number 2, and then number 3. Or you can do it automatically. You just have to know that you will get in the data in a sequential manner. And then how you manage it, you can collect them and then send them all at once. You can do that, but that depends on each application or each design. Seabird has implemented different types of specific commands. You can find this in the manuals on the internet. So there's pulse sampling, there's commands for all at the same time, do the same thing, and so forth. Here's another slide explaining the two classical techniques of bringing the signal to the central controller. The difference is one uses the ICC, the inductive cable coupler, with the architecture that I described before, where you have a jacketed cable with two grounds, one at the surface and one at the bottom. And then you need to decouple the signal and bring it into the buoy to the controller, to the IMM or to the controller. There's another way. You can bring the cable directly to this card, and then you wire the other ground pole directly, separately and parallel to the water. You can also do that, okay? It's the same thing. The only difference is that here it is the mooring cable that closes the loop through the two grounds. And here you only have, the mooring cable has only one ground at the bottom, and then you bring a separate cable to close the ground loop. You can do whatever you want. The reason why there are those options is because the problematic part of the whole thing is obviously here, where you connect the mooring cable to the buoy, which is not Seabird business. You know, Seabird helps you with components, but how to do this connection and how to best do it and manage it, that mechanically it works, it doesn't break cables, it doesn't twist, depends on each buoy design or each mooring design and so forth. That's where you have to talk to the mooring people. You know, the good news is that this technique, the inductive moorings, have been around for decades, and there's a lot of people with a lot of experience, knowledge. You don't have to start from the beginning. You can try to invent new techniques. You're welcome. The trick is just to avoid twisting, because here, for example, if you run a parallel cable and you have here some rotation or twisting, obviously you can break the cable very easily. So you have to make sure the buoy has some movement margin there. That's why maybe you want this system, you know, so it depends on those little details. But they are important, because the idea is that you want to leave the buoys out in the field for years, or for at least for a year, without any service and maintenance. and so it has to be robust. The good news is, again, that it's a metallic cable, so if you make it very thick, it's going to be very strong. The telemetry will work even with a very thin cable. So you can use inductive telemetry with just a hair-thin metallic cable. It will work, okay? So you have to decide what mechanical strength you want to have on this cable, but it works also with very thin cables. So you could think about a lot of different applications. So here, this is one of the typical connections that is used on the Pirata moorings, for example, by NOAA PML. You know, successful since 1990, so it's old business, and it's established, it's working. So here's the inductive cable. Here you see this yellow jacket. This is a plastic jacket. The quality of the plastic jacket is also important, because if it peels off, if it degrades, you get a degradation of the signal, and in the worst case, you lose the signal. So yeah, it's a materials issue. You have to select a good cable. You know, the strength of the metallic strength member has to be okay. It has to be anti-rotational if possible, and then have a good jacket that is extruded ideally onto the metallic cable, not just a separate jacket, because it will degrade easier and faster. So here you see as I say, the plastic jacket that runs into this bend restrictor, and then there is this shackle part. That's the ground. That's just this little piece is enough for being a good ground in closing the telemetry loop. Then you connect it to your mechanical connection with shackles and a chain to the buoy. This is the end of the buoy. And then they have built here some sort of tubing, like a metallic protection, with another bend restrictor type of thing. And then here it converts into a plastic tube, and inside you'll have the conducting cable. Okay, it's just one of the solutions. Another one. So in this case, they have this system where they wanted an instrument just below the surface, still being inductive. You could also, there's a lot of customers that have a non-inductive, a classical RS-232 instrument under the buoy, wired over the serial connection to the dialogger, and then separately they have the inductive line. In this case, they have decided to run the inductive line to the top and still use it for the very surface instrument. So here the same principle. So you have here, this is the plastic jacketed cable, there's a shackle, this is the ground that touches the rest of it, so it makes a bigger ground. The whole buoy is then the ground, you know. And then they decouple, they have not drawn here, below there's the ICC, the inductive cable coupler, and it decouples the electrical signal. No, sorry, this is the inductive cable spliced off and going up, and there's the inductive cable coupler just above the last inductive instrument. Okay, so you can see the little different tricks that people use, and here you can already see you always have to leave a little bit of margin, so there's the twisting and the movement of the buoy is not damaging the connections. So again, here you see the pictures. There's the ICC. This is the half of the plastic part that you already have seen. This is the detail of the instrument. So if you open up this part, you know, this is this picture here. You open up, you will find you only have 2 screws that you have to lose, and you will find the toroid. I can show you. Any questions in the meantime? Huh? So yeah, on deck what you only have to do is basically loose those screws and put on its cable. You can have them loose and you can run it through the cable while you are deploying. So while you're deploying, you have the winch, you know, releasing the mooring cable. And if you maybe have a cable counter or something, and then, you know, 1,000 meters and make a mark with a scotch, and then you can run it very quickly and mount it very quickly onto the cable. So it's easy. Those are titanium screws. You don't want to lose them. They are kind of secured with a retainer, and and here you can see the toroid. Yeah, I can take it out. You can see, you can play with it a little bit. So this part is, you don't have to break, because if you break this toroid, you have a defective signal, and sometimes you get interferences. You get rubbish onto the data strings and so forth. Yeah, so cable-wise, Seabird has some recommendations for cables, but there are several manufacturers that are specialized in inductive mooring cables. There's mooring systems, I know. They do a very good cable. It's a spin-off of Woods Hole after doing a lot of experiments. It can be kind of a little bit sound like expensive, but it's good to have good quality material. But you can do it with any type of cable. If you have a short-term mooring, you can use cheap cable, and after you do the mooring, you can throw it away. That's okay. It will work with any type of cable. But if it's long-term, you want to have good cables. Typically, you have this architecture. It's a twisted cable, anti-rotational cable, and then the polyethylene plastic is extruded onto the cable. So the polyethylene penetrates into the different wires, and it's almost impossible to peel it off. You have to really work like 1 hour with a very sharp knife to peel it off. It's very dangerous because it's very hard to peel it off. But it's very robust. You can be very, very rough with it on deck, and it won't degrade. So getting a good quality of plastic extrusion on the metallic cable is difficult. So there are not so many manufacturers that can do it. Those are another people. That's not Seabird, but it's very important to have good quality mooring cable, inductive mooring cable. And even if it works with whatever type of cable with a plastic jacket, I recommend to you to use an extruded jacket that really penetrates into the wires, into the single wires. Here are some details. So there's no limit to the communication, so you can go super deep, and we can handle thousands of meters. There's very little loss of signal. Obviously, optimum cabling has the lowest center conductor resistance and the thickest insulation. The longer cables with higher resistance theoretically need electrodes with larger surface. The electrodes are the parts that are in touch with ground at the surface and at the bottom. That's why the freshwater applications, to make sure you have good telemetry, you need to make the contact surface of those grounds bigger. What this means in practice is, if you are in salt water, if you have a shackle of contact surface, that's enough. Maybe if you want to go super sure, you can do like this or that. If you are in fresh water, you make it 1 meter. You know, it's not a big deal, and you can test it. It's easy to test before deploying. I mean, people think I have to deploy the mooring line in 2,000 meters to see if everything works. No, you can do it horizontally. So you can coil everything together and throw it into the water, or just hang it over the quay here in the harbor. and then test the telemetry. It will work the same at the surface hanging along the quay than in 2,000 meters depth or 8,000 meters depth. You know, once it works in the water, no, in the bucket, it will work in the seawater. Okay. You have to see it to believe it. That's true, because people think, well, I have to deploy it. Before I don't deploy it, I don't believe it, but it works. And then the other good news is that you can test it dry. It's very easy, because the only thing that you have to do for testing it dry is deploy the cable along, you know, on the parking space or wherever you have space, in the garden or on the long road, or coiled. You can do it coiled. It's important though that the coils don't mix, because maybe there you can induce some parasitic signal. But if you have a nice a clean coil, it will work. And then the parts that are supposed to be ground and connecting with water, you close them with a simple cable. You use a simple electrical wire you have lying around in the lab. You bring the two ends together, or you put a shackle together, or you put some copper, you know, and make a good electrical contact in the air, in the surface, and then you will basically simulate an underwater mooring. Okay. There are some little tricks and things that I'm not explaining, that you have to change the resistance selector in the electronics board and things like that, but that's in the manual, okay? But you can test everything in your lab, in your shop, lying on the ground. You can test the whole setup in the air. Then if you want to go underwater, you can do it shallow and on the quay, you know, coiled together, horizontally, whatever. And make sure that all the telemetry is robust and everything works together. And then once you're sure, you can deploy it in the deep sea. Yeah, so here is the impedance that is theoretically needed. But basically between 10 and 1,500 ohm means that whatever, you know, it means it works with whatever cable with a plastic jacket. I have tested it. I've never looked at those impedances. We have used it always with some cables to do tests or different experiments, and never really failed.
All interested.
Sorry?
Yeah.
Said someone? No, yeah. There was. Okay. So again, here we come to this component again. This is a very small component, as I say, and it's designed so everyone can integrate it. There's Teledyne, RDI, and Nortec that integrate it in series to their instruments. So you can buy ADCPs from those two manufacturers that have the Seabird inductive modem integrated into their instruments. So you can buy a Nortec current meter, an Aquadop, and clamp it onto the cable. And yeah, and this is, as I said, 1,200 baud half duplex is standard. There's a little bit of buffer here and so forth. So you make sure there is good telemetry. Yeah, this is the same thing we said before. There are some examples about commands, you know, the typical syntaxes. You can power on everyone at the same time. You can program hours and so forth. So it's very straightforward, the classical Seabird type of commands. This is the catalog that exists nowadays at Seabird. So you have all those instruments exist with inductive modem integrated. They look like similar like this. It's a classical instrument with this inductive modem cap attached, integrated into the instrument. So you have the 16 which is a CCAT recorder with CTD, optional pressure. It has up to 8 channels for analog sensors and 1 digital sensor channel. So 6 plus 1. The classical Seabird CTD type of instrument. Then you have the small 37s. You have without pump, with dissolved oxygen. All the different versions exist with inductive mooring. Then we have the 39, which is a temperature sensor. It exists with external or internal thermistor and optional pressure sensor. And then two interesting ones are the last two ones. The number 44 is the same thing as the UEMM. That's the one I gave you before, that you have to give back, by the way. The UEMM is the underwater housed version of the IMM. And the 44 is the same thing, but it has a battery, okay? Because otherwise you have to power the unit that I gave you, you have to power it externally with something. And the 44 also already comes with an internal battery, and the form factor is similar to a 37. So it looks like a 37, but it's an UEMM with battery. So here you see some examples. This is the 39 that I have here with a special net fender fairing option, because you know one of the problems with moorings is that you have those long lines, people fishing around with long lines and they get entangled, and then those nylon lines they are very resistant. They run up the mooring cable, and then they get attached to where the bracket is, and because the cable runs here and there's a space here, they get entangled here, so it breaks things. So a lot of users, they have developed some sort of net offending devices that basically when the cable comes up to here, it's kind of deflected outside and doesn't break the instrument, you know. So this is a solution offered by Seabird, but there's a lot of people doing their own stuff. So this is one of the problems, you know, fishing lines and nets and things like that. That's another story. Here you have a 37. You have the 16. You see at the top, there's the typical inductive modem coupler thing. And then there's the old RDI DVS, which I think they don't manufacture anymore. But you can buy workhorse ADCPs with modems integrated. And at the end, most of the people do it themselves, because you can buy the modems extra and do the integration yourself. So we don't know really how many other types of instruments are around. In Nortec, they offer a very well integrated version too. Yeah, so here are some examples. There are many examples. This is the Triton and the Tau and the Pirata arrays, Rama. So you see how many buoys are deployed since decades that use inductive telemetry. That's probably the main driving factor of this technology to exist. Here you can see one of those examples. This is a 37, I think, an old style 37 that has this kind of wooden or flotation material net fending thing attached to it, and an extra kind of clamps to be more robust. You know, it's a customer modified clamping device. You know. But it's a inductive standard Seabird instrument with a modified protection. And mainly it's because of the handling on deck, you know, and the net problems. So here is an interesting plot from Jamstack. So over 10 years, you see this time series. That's impressive. This little hole here, something happened. I don't know what it was. It happened, they had a problem probably at the first 150 meters, probably a cable jacket going off or something that interrupted the telemetry there. So you have, those are all the instruments from surface to 750 meters transmitting data regularly. And there's a lot of problems at the surface with the meteor, you know. Look, They had a lot of problems with the meteo sensors, but no problems with the inductive telemetry. Very funny. There's a lot of crazy and interesting and kind of science fiction applications which work, you know. The question is, of course, how long will they work? This is another story. So again, here's the concept that you have an inductive system that is traveling along the cable. So you can have an inductive sensor inside this profiler because basically you have this toroid that is able to travel. And the toroid doesn't need to be completely attached to the cable. So some people think it's important to have it really touching it, and so no, it has just to close the loop, and there can be margin for movement. So there's a lot of people using the inductive system with things that travel along the cables. So you can have sensor here traveling up and forth, and you use the gliders for communicating to the packages and downloading and acting as a hub and so forth. So this was this station Papa. So another example, here you can see, you can have everything kind of pre-mounted. That's because those instruments are kind of packed together for high resolution. And before deployment, they have kind of prepared them here on the cave. You can prepare everything very nicely packed together and deploy it very easily. In this case, you only have to be careful with not shocking too much the ferrite cores, because they can break easily and you don't see it if you don't open it. You know, so you have to be careful. So a lot of interesting applications. Those are real applications, you know, taken out from things that we got from the different customers, mainly in this case American customers, but I'll tell you some other interesting other places. This is University of Washington. You see, this is a high resolution, and they have multi-parameter systems. They have ADCPs, a lot of different things. Then they even combine it with those profilers. So there are a lot of different applications. You know, the trick is really knowing how to deploy those things. And here, that's the important part: the connection to the buoy. Here you can see another example. You see, that's the one before. You see, here's the cable protected. Here's the mooring cable, and here's the inductive cable. You have to leave a little bit of margin. There's people that use buoys that orient themselves against the wind. You have seen maybe pictures in the internet of buoys that have flaps. That normally are inductive buoys, because then they orient themselves against the wind and they don't tend to rotate too much. So that's nice to have for inductive moorings. Or you have fins underwater. There's people putting fins underwater. Or you have those type of nomad buoys that are like a ship that put the bow into the wind, and so. You know, and what else? Another one here. Again, you know, you can have a lot of resolution. There's also a lot of people that use buoys with inductive mooring lines hanging freely under the buoy. So the buoy is kind of attached with a separate chain or something that, you know, on a fixed point. And then in the middle, there is a mooring line hanging in the water without touching the ground, and serving as a telemetry line for inductive instruments. There's also people, you know, there's people using winches on buoys. I've heard there's people using winches with inductive lines. We're nearing the end. Here again, good telemetry, you know. And here probably we come, as I mentioned before, one of the problems is if you have a problem with peeling off the jacket. It happens. We had problems with big fishes. The strumming of the mooring lines, they attract apparently, for example, in the Mediterranean, we know that if you put synthetic ropes into the water, you have to be careful because strumming of the cable with the current attracts a type of kind of barracuda type of fish that has like a very sharp teeth, and they attack the cable, you know. And that's why you want to we have found the teeth in the cable. That's why we know, you know, the teeth while pulling up the cable. Oh my God, you know, there's teeth and cutting teeth in the cables. But so you want to have good quality plastic extrusion. That this is very difficult to happen. But if you have peeling off cable or damaging or something, it doesn't mean that you lose telemetry, but it can happen. If it really is a big, then what basically the coupler here understands is the mooring line is now shorter, okay? But it's easy to repair. You pull it back, you put Scotch tape on top, and that's it. You don't need to buy again 6,000 meters of cable, you know. Yeah, well, as I said, now it's kind of such a standard technology that it has been specified. We will continue to promote this. We think there's a lot of potential in that type of applications. And as I said before, I only mentioned the typical classical vertical mooring stuff, but there's a lot of other applications that we have been doing. For example, this one, it's a ship towing kind of a chain and you can control it by releasing cable with a winch. And it's easy to deconnect the different instruments. If you want to do it shallower, you can just unscrew the instrument and have it shallower and so forth. Another typical application in the industry is desalinization plants. We have been doing this a lot in the Mediterranean because of the water problem. They are obliged by law to monitor the salinity plumes. So one way of doing it is deploying a real-time system by using inductive telemetry cable through the pipes to reach the outflow area, and then they loop around the cable, just lie it on the ground with the different instruments attached to it that cover a certain area there on the stand, and then you have telemetry up to the plant through the logger. So you can have underwater observatories like that with just an inductive line, and it's cheap cable. Underwater observatories near shore always a problem because people tend to use very expensive cables with fiber optics, with multi-conductors, and then if you have a problem because of the trawlers or some sabotage or whatever or the weather, it's a big mess to repair those cables. You cannot just splice them together, you know, it's complicated. So the problem of running a cable from shore to the deeper part is always a big problem. And using simple metallic cable, which is super cheap, it can be it can be less than €1 per meter, cents per meter. If they cut it, break it or so, you can splice it together very easily. You can replace it very easily with just bolting together. And with scotching it to make the jacket again. So there's a lot of people doing underwater observatories with simple inductive cable, lying on the ground. And if it gets buried, it doesn't affect the induction. So there are many, many applications there. Another interesting applications for finishing is we will have an inductive system on the Polar Pod. The Polar Pod, you can look it up in the internet, is a French project. It's a huge free-floating kind of buoy type of manned platform that will be floating around the Antarctic for surveying the circumpolar current. And it's free-floating, has just a little bit of mobility, and it's a manned laboratory with 3 stories of laboratories. And because it's a huge structure, they will set up an inductive mooring line to the bottom of this vessel and they will be able to winch it up and down to service the instruments. But the telemetry will be inductive, you know. So there are a lot of interesting applications for it, and that's also the reason why we are explaining it, because it's not so, you know, it's not an evident thing. It's you have to understand how it works. You have to experiment it with it a little bit. You have to play around with it first. It's not plug and play really. It's more an integration thing, but it's very easy. And once you see it working, you say, wow, you know, why did I know before? It solves you a lot of problems. And you have to start thinking in a creative way how to use it for your applications. You know, there's, as I said, try to think about projects and applications for your work where you could use it instead of the classical approach. Sometimes you'll be surprised how many of those you can find. You know, you have to start, you know, thinking creatively, you know, as I said, hanging cables from buoys, laying them horizontally, towing them, having stuff going up and down the cable. There's a lot of applications there. It helps you a lot, and it's cheap compared with the alternative. Much cheaper and much more robust, and it's a proven technology. So let us know if you have any questions about it. And we can point you to experienced integrators who know the little details. Although I prevent you, everyone has his own opinion there, so we will see what is best for you. Please.
If you would like to use the swivel?
For the buoy?
Yeah. Or in your mooring line halfway, for example?
I mean, you have to solve the problem how to transfer the signal. There's people, I know that there's people that have been playing around with slip rings and things like that. But it sounds kind of complicated to me. I won't use it. I would try, I always have ended up with limiting just simply the movement of the buoy with the help of fins or a few shackles, not a long line or something. So, you know, it's kind of simple in the end. And once you have found the right design, it works, you know.
I'll add to that. So yeah, what Miguel said is right. The simpler you can make, the better. Devil Logic in Germany, they have an inductive swivel, and so they've got a stand downstairs and talk to them as well. If that's something of interest to you.
Yeah, but it's called an inductive swivel, but it's just a normal slip ring, you know, in a format that allows you to rotate and maintain the connection. So yeah.
Two technical questions. You said the watt rate is 1,200, I think. Is this a fixed value, or can this be moved higher or lower depending on the positions?
No, it's fixed.
Okay.
It's fixed by the hardware, right?
And the other one, on some of your graphs, you had the number of windings for the toroid or for the wire of the toroid for different values. Is this a significance behind that?
I don't know the history about that. Maybe you can comment.
Yeah, so we have what's called a 20-turn coupler and a 100-turn coupler. The primary difference is current, right? So if you have a system that is really power sensitive, where you don't have a lot of solar panels or battery, when power is your main thing, you want to go to the 100-turn coupler. The most common is the 20-turn, gives a good balance, it's more robust. So if you think about it, the more current you can put on there, the less sensitive you are to inductive interference or anything, ships going by. So 20-turn coupler is 95% of the applications. 100-turn really when you have power as the main concern.
Yes, I forgot to mention one thing. Of course, you have to remember the principle, which is induction. So if you have a current inducing on metallic parts and conducting parts, you don't want to have interfering metallic parts touching or interfering inductive-wise with your system. You know, so there's always kind of discussion and some doubts about when you run, for some of the inductive cable through a metallic pipe. Imagine a metallic pipe. Does the induction work there? Well, it depends on the distances, where the cable is. You don't want to run it into a metallic pipe in principle, but it could work, because if the cable is far away enough, it will work, because the induction is really local, you know. But of course, there's an electromagnetic field spreading out there. And so you have to take care, you know, don't forget there's an electromagnetic inductive field out there operating. It's very low intensity, you know, and very low signal, but it can be a problem if you have some metallic part touching or something like that. Anything else? Okay, so if you have any questions, please call Siebert or us or whatever. And
Miguel is a great resource in Europe. So he travels kind of everywhere. He's got system integration experience, GUI experience. So we refer to a lot of customers who have questions about inductive mooring systems in this area to Miguel. He's kind of our expert. But certainly contact Siebert if you have questions. We're down at stand L9, so come take a look. We've got our instruments there, and any questions you think of will be here for the next 3 days.
thank you very much.
Thank you, everyone.